So welcome everybody to today's meeting of the Western Hemisphere Virtual Symplectic Seminar. And before we get to the talk, I want to just mention that today and our meeting in 2 weeks are both sort of events on the topic of Fluorohomotopic theory. So Ralph Cohen's giving a talk today, and then in 2 weeks, we're having a panel discussion with 7 esteemed experts. We're really excited about that. And we are crowdsourcing some questions. So I'll put the link in the chat after the talk begins. And if you'd like to submit a question in advance, you're very, very welcome to do so. Okay, so without further ado, we're really happy to have Ralph Cohen from Stanford here to tell us about Fluorohomotopic theory. Take it away, Ralph.
Okay. I am now getting a lot of interference.
Yeah, I think it's okay. I think that's it.
Oh, okay. Good, good. Well, thank you, Nate. It's a real pleasure. I appreciate the invitation to speak in the seminar. As Nate said, the title is Fluorohomotopic Theory, Old and New. And, whatever my contributions were, they were to the old part. Back 25 to 30 years ago, my collaborators and I were really quite interested in understanding the homotopical foundations of what was Floer homology, what was a brand new theory at the time. And what I'd like to do today is tell you about some of our thoughts back then and how they developed. And then the really exciting stuff, at least for me, has been watching in the last several years the development of the Fluorohomotopic theory and its applications to several problems in symplectic geometry and in low-dimensional topology. Okay, so let's get started. So in a paper that my collaborators John Jones and Graham Segal and I published in 1995, and this was in the Floer Memorial volume, we coined the term Fluorohomotopic theory. And the proposal in that paper was to attach a homotopy type, actually a stable homotopy type, to the geometric data given in some version of Floer homology. And in general, we asked the question, when is the Floer homology isomorphic to the singular homology of a naturally occurring space? Or really, as it turns out, it's more natural to study the stable homotopy theory, and the objects of study are spectra. And I'll say a little bit about why in a few minutes. But anyway, when is it isomorphic to the homology of a naturally occurring space or spectrum that is defined in terms of the geometric properties of the moduli spaces that occur in the Floer theory? So we gave a proposal for how to construct such a homotopy type when certain conditions were met, and we gave some rather simple examples, but really it was quite a few years that passed before the notion found some genuine applications. So as I said before, I found that very exciting. So I hope to say a few words about that at the end of the talk. And as Nate said, this will be discussed much more apparently in the panel discussion in a couple of weeks. So so let's get started. As you know, in 3 seminal papers in the late 80s, Floer introduced what were Morse theoretical homological invariants that really transformed the study of low-dimensional topology and symplectic geometry. In those 3 papers, in one of them, he introduced the notion of instanton homology for 3 manifolds, which has the property that when you pair them with Donaldson polynomials of 4 manifolds, one gets a 4-dimensional topological field theory that really revolutionized the study of low-dimensional topology using gauge theory and eventually Seiberg-Witten theory and so on. In another paper, he defined what's known as symplectic or Hamiltonian Floer homology and allowed him to prove a well-known conjecture of Arnold on the number of fixed points of a diffeomorphism arising from a time-dependent Hamiltonian flow. And I'll say more about that later because there have been recent developments along those lines too on that problem. He also introduced a notion of Lagrangian intersection Floer homology for the studying of how Lagrangian submanifolds of a symplectic manifold can intersect. And so they're really very, very important papers. Yeah, since that time, as you all know better than I do, there have been other versions of Floer theory that have been introduced in symplectic geometry and in geometric topology, such as Hegardt Floer homology and not Floer homology and others. And the rough idea in many of these theories is to associate a Morse-like chain complex that's generated by the critical points of a functional that's typically defined on an infinite dimensional space. And the fact that it's infinite dimensional is what makes it hard analytically. But let's get started by looking at the classical case of a Morse function on a closed compact Riemannian manifold. Then one gets a Morse chain complex where the chain CP is generated by the critical points of the Morse function of index P. And if the metric, the Riemannian metric on the manifold is chosen, there's a generic choice of such, to have a Morse-Smale transversality property, then one can compute the boundary homomorphisms explicitly in the following way. And this is really a quite important concept, namely that if you have a critical point of index P, so we think of that as an element of this chain group, then the boundary homomorphism will be a linear combination of index P minus 1 critical points, and the coefficient will be determined by the moduli space of gradient flow lines that connect A to B. And in this generic situation, this generic choice of what's called a Morse-Smale metric, that moduli space will be zero-dimensional, it'll be naturally oriented, and so you can count the number of points, and that's the coefficient in the chain complex. Now, one can do this algebraic topologically without choosing metrics and so forth. Indeed, the Morse complex is actually the cellular chain complex of a naturally occurring CW complex that I'm calling XF of the homotopy type of the manifold. It's often diffeomorphic or homeomorphic to the manifold. So I am hearing something, but I don't know if there's a question, but I can't understand it. The sound is.
Okay.
I apologize. I just can't understand what you're saying. So maybe toward the end, the questions can be assembled, and I can address them then. The sound is just not good, at least for me. Anyway, this CW complex has one cell of dimension lambda for every critical point of index lambda. And you've all seen this, it's in many textbooks. And the attaching maps, how the cells are attached together, was studied by John Franks in the 1970s. And what we did, Joan Segal and I did, in the early 90s, I viewed it as a continuation of that study, trying to understand the attaching maps of these cells, not only from a point of view of algebraic topology, but also from a geometric point of view in terms of manifold theory. And I'll talk much more about that. So this led us to the natural question. In Morse theory, the chain complex is the cellular chain complex of a CW complex. So we ask the same question, is that true in Floer theory? Is the Floer chain complex, does it arise as a cellular chain complex of a CW complex or a CW spectrum? And we ask, more specifically, what properties, geometric properties of the data of the Floer functional, namely its critical points, the gradient flow lines that connect them, what properties are needed in order to define a CW spectrum that realizes this Floer chain complex? And it actually led us to what we thought was an interesting question purely in algebraic topology that says, well, given any chain complex, we'll start with a finite chain complex, but we also addressed infinite chain complexes. Is there a reasonable way to classify the CW complexes or CW spectra that realize this complex? Purely a question in algebraic topology, which we would hope would have applications to Floer theory. So let me start with what we did with this question in algebraic topology. It's classical homotopy theory, meaning it goes back to the methods of the 1950s. So what do we mean by realizing a chain complex? So let's start basically with like we have in Morse theory, a finite chain complex, where each chain group is finitely generated free abelian group. And let's assume it has a basis. It's given a basis. So for example, in Morse theory, that basis is the set of critical points of that index. Now let's work backwards. Suppose we do have a CW complex that realizes that chain complex. So what would that mean? So we'd have a filtered space. It's filtered by the skeleton of the CW complex. Let's call the quotients of that skeleton Ki, Xi mod Xi minus 1. And notice that in this setting of a skeletal filtration, Ki is a wedge of spheres of dimension I, and the number of spheres, that spheres are indexed by the elements of that basis. And in particular, the reduced homology of Ki, these subquotients, is the chain group Ci. So the chain group immediately tells us about the subquotients of a space or a CW complex that might realize it. It's kind of like in group theory, knowing about the composition theory of composition series of a group without knowing the group itself. There may be many groups with the same composition series. There may be many and are many CW complexes, CW spectra with the same subquotients, with these same KIs. Now here's a trick of classical homotopy theory that many of you are familiar with. It's one of the tricks of the trade. And that is these KIs, which are the subquotients, Xi mod Xi minus 1, instead of thinking of them as subquotient, as modding the Xi minus 1 to a point, let's think of them as a mapping cone. So you take Xi minus 1, viewed as a subspace of Xi, and take the cone on that subspace. It has the same homotopy type. Instead of modding it to a point, we just take the cone. Why one does that is then the quotient map, the map from Xi to Ki, where you mod out by Xi minus 1, can be viewed as homotopic to an inclusion map, where you include Xi into the complex you get by coning off the subspace Xi minus 1. So it turns a quotient map into an inclusion map. As I said, this is a standard trick of the trade. You can turn in homotopy theory any map into an inclusion and keep the same homotopy type. Now, when you do that, you can then take the quotient again, except now let's take the quotient by Xi. And so what one is left with is you have the cone on Xi minus 1, and the base of that cone is squashed to a point, so you're left with the suspension of Xi minus 1. So this is the so-called Barrett-Pupa extension of a cofibration sequence. Cofibration sequence is, in this setting, just a fancy term for an inclusion, Xi minus 1 into Xi with quotient Ki. But now with this process of changing quotients to mapping cones, you can extend it to a new cofibration sequence, xi to ki, which we think of as an inclusion, where the quotient is the suspension of xi minus 1, and so on. And the reason one does that is that you can define a map called delta I from ki to the suspension of ki minus 1, which is you look at that quotient map that I just described from ki to suspension of xi minus 1, and then you look at the next quotient map to the suspension of ki minus 1. And that map induces the cellular boundary homomorphism in the cellular chain complex. Because you look at that map in homology, in dimension I, that's the ith chain group, and then you follow it to the homology of the suspension of ki minus 1, which is ci minus 1, and that's the boundary homomorphism when you have a CW complex. You've all seen that. It's described in almost every algebraic topology textbook. So with this, one can make a definition. One can say that a finite CW complex or spectrum realizes a chain complex if its cellular filtration satisfies the following properties. The quotients have homology equal to Ci, the chain groups, and the induced map in homology from this construction is equal to the boundary homomorphism. So the chains determine the subquotients, and the boundary homomorphism determine these, at least in homology, these attaching maps. But of course, there's much more in a CW complex or a CW spectrum than just this data. And so that's what we wanted to do, is to classify those CW spectra that realize this chain complex. And the way we went about it, again, using very classical techniques, was to observe that if you model a chain complex, which is algebra, by homotopy theory, you get something more interesting. So we have these maps that I just defined from Kn to suspension of Kn minus 1. And so you can iterate that to the suspension, twofold suspension of Kn minus 2, threefold suspension of Kn minus 3, and so forth, all the way down to the n-fold suspension of K0. And we call that, we observe that that's a homotopy chain complex in the following sense. It's not true that, I mean, it's not sensible to say that the composition of these boundary maps is 0. There's no algebra here. There's no 0 to be had. But it is canonically null homotopic. The cones that we attach, a little exercise for you to see, is that when you compose them, they're naturally null homotopic because you go along a cone and you end up at the north pole of that cone, and that gives you a null homotopy. So how do you use that null homotopy? What information does that null homotopy give you that just saying it's 0 doesn't give you? Well, you can take the cone on one of these iterated suspensions of one of the Ks, and you can map that cone to Kj minus 1 by that null homotopy. A null homotopy is really an extension to a cone. So you can map that cone to it. Now, of course, you can also map Kj to Kj minus 1 by just delta J. And so you get this map of this slightly more complex to Kj minus 1 using that null homotopy. And more, I won't bore you with all of the details here, but as I say, it's rather direct and it's very old-fashioned. You get a map from a more complicated complex that involves iterated cones of suspensions of one Kj to another Kj. So you get all these maps from these iterated cones of suspensions to other Kjs. That's the attaching data in a CW complex. And I'll call them phi PQ for a map that this procedure gives you. And it's I've indexed them here properly. It's an iterated cone of an iterated suspension of KP to another iterated suspension of KQ. So those are the higher order attaching maps. Notice when Q equals P minus 1, this is just that map delta that I described a moment ago. So we call these the higher order attaching maps. And again, reinterpreting old homotopy theory of James and Whitehead and gosh, I don't even know who else, from the 1950s, it's possible to show that this attaching data, these maps, completely determine the stable homotopy type of X. They don't quite determine the homotopy type of X, but they do determine the stable homotopy type of X, which is the first reason that we chose to go into the world of stable homotopy and work with spectra rather than spaces. But if you're not familiar with spectra,
Ralph, if you don't mind, let me pause you for 1 second.
sure.
There's a question from an anonymous audience member who asks, is it possible at this point to kind of explain how what you've done so far can be interpreted in terms of the original Floer theoretic motivation?
Yes, and I'm about to get there, but the idea is, can one construct from the Floer data a underlying homotopy type that reflects that Floer data, which would in particular have a chain complex that is the Floer chain complex. Now, so we did it in 2 steps, and what I've been describing is the first step. The first step is the algebraic topology. How do you construct the homotopy theory that underlies any chain complex, irrespective of where that comes from? And the second step, which I'll get to in just a second, will take that underlying homotopy theory and convert it to manifold theory, where it is potentially more usable in the Floer theoretic setting. So that's what I'm trying to do.
Thanks, Ralph.
Okay. So anyway, we have these collection of attaching maps, and the question is, how do you organize them? How are they organized in such a way that you can say this collection of attaching maps that are coherent in some way or another classify the CW complexes or spectra that realize a chain complex? And to do that, we did it functorially. And we defined a category we called script J, where the objects are just non-negative integers, and the morphisms from I to J, well, there aren't any if I is less than or equal to J, and if I is bigger than J plus 1 anyway, the morphisms you get, it's a topological space. It's you take vectors of length I minus J minus 1 of non-negative real numbers, and then you take that space and compactify it. You'll see why we choose that in just a second if you hang in there with me. And one way to think of that is you can think of them as sequences of numbers where those most of the entries of that sequence is 0 unless K is between I and J, and in that case, they are non-negative, and then it's compactified. You'll see why we chose that space in just a moment. But, I should say, when you think of them in sequences that way, then composition of morphisms is just simply adding the sequences. So it has that natural composition. So what we proved is that the realization of a finite chain complex, and this is purely algebraic topology, corresponds to functors from this category to finite spaces or spectra that on the level of objects assigns to an object these subquotients, these wedge of spheres. There's one more condition that I'll get to in just a second. On morphisms, notice what it does. It takes the smash product of this morphism space with Zm, and it produces a map to Zn, because for every morphism in here, you get a map from Zm to Zn, which is a map of spheres. But this smash product, and this is why we took the one-point compactification of these vectors of non-negative numbers, this is a wedge of iterated cones of spheres. So this data is a way of encapsulating maps of iterated cones of spheres to spheres, namely the higher order attaching maps that I mentioned a few minutes ago. So that answers the question on the algebraic topology side. And whoever asked that question was absolutely right to suggest there's no geometry yet. There's no even differential topology yet, no manifolds in sight. I should say, when n equals n minus 1, you have maps of spheres of the same dimension, and those are determined by the boundary homomorphisms. So all the higher order attaching maps are included in this functorial data. So again, this is all algebraic topology, which this is what I was raised on, and I love it, but it doesn't address, at least not directly, the question of how you can study something deeper than Floer homology. So this goes to the question of how are geometric topology and stable homotopy theory related? And for any such question, you go back to work of Pontryagin and Thom on cobordism. In this case, we're going to go to work of Pontryagin, which goes all the way back to the 1930s. And just to say what I'm going to do before, I want to translate all of this data about maps of spheres and iterated cones of spheres to other spheres, these higher attaching maps, to statements about the moduli spaces that occur in Floer theory. And so let me describe how we're going to do that. So first of all, we need the notion of a framed embedding of a manifold. So suppose you start with a closed N manifold, then a framed embedding of that manifold into Euclidean space is an extension of that embedding to the manifold across a disk. The disk has the right codimension, which is a diffeomorphism onto its image. Another way of saying that is you're identifying the tubular neighborhood of that embedded manifold with the manifold across a disk, or saying it another equivalent way, you're choosing an isomorphism of the normal bundle with the trivial bundle, which of course may not always exist. But that's what a framed embedding would be. When you do have a framed embedding, Pontryagin original construction is what's now called the Pontryagin-Thom collapse map. You take the sphere of the ambient dimension, viewed as a one-point compactification of Euclidean space, and then you mod out everything outside the image of that embedded manifold across disk. In other words, everything outside the tubular neighborhood gets modded to a point, and what you're left with is the one-point compactification of the tubular neighborhood, in this case, M cross a disk. Then you can project onto the disk part, and you get a sphere. So you get a map from a sphere of the ambient dimension to the sphere of dimension k, the codimension. Conversely, if you're given any old map from one sphere to another, and you assume that it's transverse to, say, 0, then you can pull back the 0, and that'll be a manifold. Embedded in the sphere, it stays away from infinity, so you can think of it as embedded in Euclidean space. And it's equipped with a framed embedding, because if you pull back a little ball around the origin, you get a manifold across a disk embedded in that Euclidean space. And that establishes Pontryagin. Oh, I apologize. It should have turned. I assume you're all hearing this. I should have turned off my phone. I apologize. And now I seem to have lost my Zoom page. Hold on a second. I apologize for this.
And we can still see your slide.
Oh, that's funny that I can't for some reason.
If you're, are you on a?
I think I have them now. Okay.
Okay.
Yeah, so that was a little bit weird. Thanks. Anyway, so this establishes Pontryagin's correspondence between the homotopic groups of spheres and framed cobordism. Namely, if the pi n plus k of sk for k large corresponds to framed cobordism classes of framed n-dimensional manifolds. Framed, and one way to think of framing means finding a framed embedding into Euclidean space. So of course, not all manifolds have that property. Now, an alternative viewpoint of what Pontryagin did was to say complexes of the form of sphere union a disk for k large are classified by n-dimensional framed closed manifolds. So here's a relationship between the kind of objects we want to study, CW complexes or CW spectra, and manifolds. But in this case, for closed manifolds, all you get is an understanding of complexes of this rather simple type, a sphere union a disk. So what about more complicated complexes? And that was the original question. How can we understand those in terms of manifold? And the answer is you need the notion of framed manifolds with corners. And you can do the analogous thing to what Pontryagin did, except now, like we had before, you're mapping an iterated cone of one sphere to another sphere. Rather than just simply mapping one sphere to another, you take an iterated cone. And the reason, and one way to think of that is you take this space that I mentioned earlier, R plus the non-negative real numbers, n minus m minus 1 copies of that, which is the dimension of the cone coordinate across Ri, compactify that whole thing, and you get the iterated cone of a sphere, and you map it to compactification of Rj, which is another sphere, and you assume it's smooth, and you pull back a regular point, and you get a framed manifold with corners embedded in a framed way into this framed Euclidean Euclidean space with corners, namely some number of coordinates that have boundaries to them. So that's what a framed manifold with corners is, and you get that data. It's also framed by pulling back a small neighborhood and so forth. So you can ask the question, well, a moment ago, I described this pure homotopy theory. How do we describe or classify CW spectra that correspond to a chain complex? But now how can we do it in terms of framed manifolds of corners? Because this is where there's a chance that it might be applicable to Floer theory. So the notion we came up with was to describe a framed flow category. So what this is a topological category whose objects form a discrete set, and you should think critical points of some functional, and whose morphism spaces are compact, smooth, framed manifolds with corners. The type we just studied, because using Pontryagin ideas, because those are what apply to these maps of iterated maps of cones of spheres, which are what the attaching maps of CW complexes are. The only other condition has to do with the composition maps have to be embedded into the boundary, and the boundary has to be filled up by these composition maps in a natural way. So that's what a framed flow category is. It's just a category where the morphisms are the framed manifolds with corners. And the archetypical example to think about is the category, the flow category of a Morse function, where the objects are the critical points, and the morphisms are the piecewise flow lines connecting the critical points. And that's the compactification of the gradient flows that connect the critical points. So that's the example to think about.
Ralph, can I ask a question?
Sure.
Yeah, this is maybe totally off base, but the last condition in the definition saying that every point of the boundary must be in such an image, is that at all like a cofibrancy condition?
You might be able to interpret it that way, but we put it in there because, frankly, we didn't want to have to deal with phenomena like bubbling. And one might generalize this notion to allow for it. But in our first pass at trying to establish this theory is let's work in a situation where you don't have any bubbling other than the kind of gluing phenomena you have, like in Morse theory.
Okay, and sorry, I'm being dense, but how does that condition exclude bubbling?
Well, it says that the boundaries of these moduli spaces are just defined in terms of these glued moduli spaces of lower dimensions. There's no other bubbling or other phenomena occurring in the boundary.
I see. Okay. Okay. Thank you.
Sure. Okay. Let's see. Now, we need a genericity condition that's analogous to having a framed, having a Morse-Smale condition on the metric. So we say that the framed flow category is Morse-Smale if you have a couple other properties satisfied. One is that the objects are partially ordered by saying A is bigger or equal to B if the morphisms from A to B are non-empty. Rather simple idea, but thinking of it in terms of flows of a Morse function, what it says is that if you can flow from A to B, then you can't flow backwards. And that's a Morse-Smale property, assuming A is not equal to B. But then we also have the condition that the only morphism from an object to itself is the identity morphism. And that's just saying there are no loops of flow lines. And again, that's a Morse-Smale property. Finally, we need an index type map, which is just a set map from the objects to the integers, which preserves this partial ordering and keeps track of the relative dimensions of the moduli spaces. That the if you look at the morphisms from A to B, the dimension of that moduli space will be the difference of these indices -1. So that's the Morse-Smale property. And then the theorem we proved is that if you have such a framed flow category with this Morse-Smale property, then you get a functor, this homotopy theoretic construction that I mentioned a few minutes ago, and therefore you get a spectrum that realizes that chain complex. So you go from framed flow categories, framed manifolds with corners, to CW complexes or spectra that realizes a chain complex. So that's the setting in which we wanted to study Floer theory. In this, the boundary homomorphism will be the usual, have the usual description now, where in this case, it's kind of interesting, a trivial thing, but it's still interesting. The dimension of the morphism spaces when the relative index is 0 is 0. And it's because that moduli space is calculated by the Pontryagin classification, which is an element of the homotopic groups of spheres, pi k of sk, which is the integers. So that's the integer that goes there. Of course, you can think of that as an orientation too, and that's probably the more conceptual way to think of it. But I just wanted to point that out. So I really want to emphasize this point. In a framed flow category, the objects in the zero-dimensional morphism spaces are determined by the chain, determined by the chain complex. All the higher dimensional morphism spaces reflect the higher dimensional geometry and topology of the moduli spaces that may occur in a Floer theory or some other theory. So that's the point. The point of Fluorohomotopic, let me just say this again and jumping up and down. The point of Fluorohomotopy theory as opposed to Floer homology is that the goal is to use the topology of the higher dimensional moduli spaces to gain invariance and not just the zero dimensional ones. That's the idea.
And I see that there's a question from Weiwei Wu. Weiwei, you can go ahead and ask it.
Oh, I just want to ask so if you define the morphism between A, B to be the compactive moduli space with operand, so does this fail anywhere?
I apologize. I could hear it in terms of volume, but it just was very muffled.
Yeah, I think that Weiwei is asking if you relax the definition in terms of that boundary property, so you do allow for some kinds of bubbling, might it be possible to still prove that theorem?
Well, I think that's an important idea, and I think that is potentially an important bit of research to be done. I think it's much, I'm an algebraic topologist, and I think that becomes a question of geometry and analysis, how to handle the bubbling and how to put it. The point is we wanted to take advantage of the Pontryagin-Thom theory that relates the attaching maps of cells to frame manifolds. When you put in bubbling, you go out of the realm of frame manifolds, or you go out of the realm of manifolds, and it's a whole new ballgame. It's become much more difficult geometrically and analytically, but that's not to say something can't be done.
Yeah, thank you.
So in fact, I put this in my slide. So we were frankly quite pleased with this construction, but one problem immediately in its applicability is that the moduli spaces are often not smooth, and even if they are, they may not have framings. The moduli spaces that come from Floer theory. That's the basic problem. But we did talk about a couple simple examples, and as I mentioned before, the flow category of a Morse function on closed manifold is classical setting. You get this frame flow category, and when you go through the process of getting this functor out of it and getting the CW spectrum, you just get the manifold back again, as you'd expect. So the Floer homotopy type of a Morse function, the homotopy type is the homotopy type of the manifold, and you get all the attaching maps, like the handle body decompositions of the manifold. A bunch of years later, about 15 years later, I found another example where if you take the cotangent bundle of any manifold with its canonical symplectic form, and you have a time-dependent periodic Hamiltonian and a compatible almost complex structure, then for a generic choice of H and J, you can prove that there is indeed a frame flow category. And all of this theory works, and the stable homotopy type you get, in other words, the Floer homotopy type of the cotangent bundle, at least when M is spin, is the suspension spectrum of the free loop space of the manifold. That generalizes the theorem of Viterbo, who computes the Floer homology and shows it's the homology of the free loop space when it's spin. When it's not spin, you still can do this, but you get Thom spaces over the free loop space. And in fact, it's kind of interesting, more from an algebraic topology point of view, is that if you change a natural question is, what if you change the framings of these manifolds? that doesn't change the Floer homology, or in the first case, the Morse homology. But if you change your framings, it changes the homotopy type. And what you get are actually Thom spaces of vector bundles over the manifold, sort of like twisted copies of the manifold. By the Thom isomorphism theorem, at least if they're oriented, they have the same homology, but they have different homotopy types. All right, so I'd like to spend the remaining time talking about more interesting and modern applications of Fluorohomotopy theory. And I'm just going to say a few words about a few examples. I know you're going to be studying Fluorohomotopy theory in more detail in a couple of weeks. But you know, one of the interesting works was that of Lipshitz-Sarkar on Cohen homotopy theory a few years ago. They studied the homotopy theoretic foundations of Cohen's homological invariance of knots and links. And as many of you know, the Cohen homology is a bigraded abelian group, but is computed from a chain complex that's defined in terms of a link diagram. And the chains have to do with all the various ways of resolving the crossings in that link diagram. But the homology groups don't depend on that diagram. They're just an invariant of the isotopic class of the link. And their work, the idea was to associate to this link diagram a family of spectra whose homotopy types, full homotopy types, are invariants of the isotopic classes of the link. And that the Cohen homology would be the reduced singular homology of these spectra. And they accomplished this. And they did this by associating a framed flow category to moduli spaces associated with the link diagram, which had to do with various ways, or all the ways, of resolving the various crossings in a link diagram. And so they get a Cohen homotopy type, and it's had several interesting applications. You know, one immediate application when you have a Floer homotopy theory, like this example, is that the cohomology gains extra structure. It becomes a module over the so-called Steenrod algebra. Just having a chain complex is not enough to give you that module structure. So Floer homology doesn't come equipped naturally as a module over the Steenrod algebra. But once you have an underlying homotopy type, it does. And they showed that that by actually calculating some of the operations, that it's a non-trivial module structure for even some very simple knots, like torus knots. And right just beyond that, Seed showed that, in fact, there are pairs of links that have isomorphic Cohen homology, but those isomorphisms are not as modules over the Steenrod algebra. So they have distinct Cohen homotopy types. So that's a rather interesting distinction. Same homology, but different homotopy types as seen by the Steenrod algebra. Another application is, as many of you are familiar, Rasmussen constructed a sliced genus bound called the S invariant using Cohen homology, and using the Cohen homotopy type, Lipshitz and Sarkar produced a family of generalizations and got even stronger sliced genus bounds. And finally, Stoffregen and Zhang used this homotopy theory to describe rank inequalities in Cohen homology for certain links. Now, I was going to go into the definitions more, but I think a better use of time is to talk a little bit about a couple other examples of application. One was a really dramatic example of a work by Ciprian Manolescu just a few years ago, where he solved the triangulation problem using an equivariant version of Floer homotopy theory. And he answered a question that is 95 years old, the question of Kneser, natural question, does every topological manifold admit a triangulation? Which is to say, a homomorphism to a simplicial complex. Natural question. Now, in more modern terms, one can ask a stronger question and ask whether every manifold admits a combinatorial triangulation. And that means that it's homomorphic to a simplicial complex where the links of the simplices are spheres. That structure is equivalent to having a piecewise linear structure, PL structure. So you can ask, does every topological manifold admit a PL structure? So it's a stronger version of this triangulation question. So a little bit of history. In the 20s, Rado showed that surfaces admit combinatorial triangulations, and in particular triangulations. And in the 50s, Moïse showed the same thing for three manifolds, topological three manifolds. But earlier than that, Cairns and Whitehead showed that smooth manifolds of any dimension have this PL or combinatorial triangulation structure. So this question is really a question about topological manifolds, not a question about smooth manifolds. And in somewhat more modern times, in the late 60s, Kirby and Ziebenman showed that there exist topological manifolds that don't have PL structures. That, in other words, that do not have this combinatorial triangulation in every dimension greater than 4. And they produced an obstruction, the Kirby-Ziebenman obstruction, which lives in H4 of the manifold with Z2 coefficients. Now, the first counterexample to the original triangulation question, simplicial triangulation conjecture, was given by Casson in the late 80s, I think, who showed that Friedman's four-dimensional E8 manifold, which he showed did not have a PL structure. So Friedman showed it did not have a combinatorial triangulation. Casson showed did not even admit a simplicial triangulation. So that was first answer to Kneser's question, and the answer is no. In dimension 4, not every 4 manifold admits a triangulation. But the general question that Kneser asked in dimensions 5 and larger was not achieved until a couple years ago with Manolescu's work using equivariant Seiberg-Witten Floer theory, Fluorohomotopic theory. And I'd like to sort of describe, I mean, this was a monumental result. So, and I know many of you have heard lectures on it, but I'd like to just sort of describe a very rough structure of the proof so you can see where the Floer theory comes in. So suppose you have an N manifold that is equipped with a homomorphism to a simplicial complex. Then you have the Kirby-Ziebenman invariant in H4. And there's another invariant called the Sullivan-Cohen, different Cohen-Sato class, C of K, which is in Hn-4 or H upper 4 cohomology of the manifold with coefficients in the Proportism group of homology 3 spheres. It's a funny group. And what you do is you take a linear combination, look at all simplices of codimension 4, and you look at their links. If they were combinatorial triangulation, those links would all be spheres, and so would be 0 in this group. But in general, they're elements of this group, and that becomes an obstruction. And then one uses the Roclean homomorphism, which is a homomorphism from this group of homology 3 spheres to Z mod 2, defined by the Roclean invariant of a homology 3 sphere is you take a 4 manifold who has that 3 sphere as a boundary, or the homology 3 sphere as its boundary, and you look at its signature, divide by 8, and he proved that that's well defined, mod 2. Now, any short exact sequence gives you a long exact sequence in cohomology. And it's known that the Roclean homomorphism takes this Sullivan-Cohen Sato invariant to the Kirby-Ziebenman invariant. So in particular, one can conclude that if the manifold admits a simplicial triangulation, and that was the assumption up until a second ago, then the Kirby-Ziebenman invariant is in the kernel of this boundary homomorphism. So that becomes an obstruction. And the really cool theorem that was proved some years ago by Galuski and Stern and also Matsumoto, that a closed manifold of dimension 5 or greater admits a triangulation if and only if this boundary homomorphism of the Kirby-Ziebenman class is 0. So if the Kirby-Ziebenman class is 0, it admits a combinatorial triangulation. But even if it's not 0, if it becomes 0 after you apply this boundary homomorphism, it admits a simplicial triangulation. Now, doing a little bit of algebra, now you can notice that that connecting homomorphism in that exact sequence would be 0 if that short exact sequence that I described before, this one, were split. There was a splitting. Then if that were the case, the Galuski-Stern-Matsumoto theorem would say every topological manifold of dimension 5 or larger would be triangulable if it were split. And the amazing result, again, due to the same people, is that there exists non-triangulable manifolds of every dimension greater or equal to 5, if and only if that exact sequence does not split. Now, in earlier work, Manolescu defined a monopolar Seiberg-Witten version of Floer theory of, in fact, an equivariant Floer stable homotopy type. And using that Fluorohomotopic theory, he was able to show that the exact sequence does not split. And the strategy, just in very simplistic terms, is the following. If you had a splitting, then the image of that non-zero class in Z mod 2 would represent a homology 3-sphere of order 2 with a non-zero Roclean invariant. And it's easy to see that that if that were to happen, there could be no lifting of the Roclean invariant to the integers. The Roclean invariant takes values in Z mod 2. If it lifted to the integers, then there could be no such splitting. And that's what Chyprin was able to construct using a pin 2 equivariant Seiberg-Witten Fluorohomotopic theory. So that's a very rough 30,000-foot view of the structure of his proof. Now, I have maybe 2 minutes, which is not doing it any justice, but I feel a little better because I know you're going to have this panel discussion in a couple of weeks, and I'm sure this will be discussed. But very recent work of Abouzaid and Blumberg on the Arnold conjecture and Morava K theory is really quite dramatic. And it's dramatic not only in terms of the theorem they get, and basically, I think I won't use the slides anymore. Basically, the theorem says that, Arnold proved that the number of fixed points coming from a time 1 periodic Hamiltonian were bounded below by homology, where Arnold actually conjecture is that it's bounded below by the maximum number of critical points of a Morse function. Now, so what Floer proved and others extended is not the full Arnold conjecture. And Abouzaid and Blumberg proved this conjecture for a certain kind of generalized homology theory using Floer homology called Morava K theory. And aside from being an extremely interesting piece of work, their work is actually very detailed and very long. It sets up the foundations, both in the algebraic topology and in the geometry and analysis, the symplectic geometry of Fluorohomotopic theory. And it tackles the question that I asked a moment ago: what if you don't have smooth moduli spaces? In this case, you don't. However, in this case, the moduli spaces do have reasonable compactifications as orbifolds. In fact, as quotients of manifolds by finite group actions. And Morava K-theory has a feature that it satisfies Poincare duality even when you divide out by finite group action. So that was one of the applications. They also took on the problem of the moduli spaces may not be framed. In this case, the moduli spaces are not framed, but they do have almost complex structures, which was enough to prove this theorem. So anyway, the main thing I want to mention is that this is a very exciting new area to work in, and the foundations are in place and good references. I mean, you could look at our old paper for motivating ideas, but if you want serious detailed references, read the Abouzaid-Blumberg manuscript. So I wanted to say that. And I will quit here. Thank you very much.
Okay, let's give Ralph a hand for a really beautiful talk.
Thank you.
And let me open the floor to questions. So you can put something in the chat and I'll call on you, or you can just unmute yourself. And maybe I'll start off with one. I was wondering, back in the 90s when you did the original work, was your motivation more from the perspective of understanding Floer theory as an algebraic topologist, or was there some particular application that you had in mind?
You know, it was kind of interesting. During that time, Morse theory, people were taking a second, third, fourth look at even classical Morse theory. Witten wrote a paper describing the Morse complex, for example. And Floer's paper came out, and then, you know, as an algebraic topologist, our immediate thought was, well, wait a minute, the Morse complex is just the cellular chain complex of a chain complex. Why is that a big deal? And then Floer theory came out in the late 80s, and it became clear why it's a big deal, because here in Floer theory, you had these new invariants in symplectic topology and in low-dimensional topology that were not the chain complex, coming from the chain complex of a CW complex. So that just led to the question, well, are there homotopical foundations behind what Floer did that one could describe? And so that was the motivation for our thinking about this question.
Okay, thank you. Okay, any questions from anyone besides myself? Ralph, would you mind another question from me?
Not at all.
Okay, and you're under no obligation to answer this question, but I'm curious. You've been talking in the later part of your talk about some applications that others have been making using Fluorohomotopy theory. Do you have any hopes about the direction that things go in, or any particular questions or types of questions that maybe one could approach at this point using Fluorohomotopy theory?
You know, to be honest, that's really beyond my expertise. I find it exciting that the questions that stumped us, the foundational questions about what do you do if you don't have a framing? What do you do if you don't have frame manifolds of corners, but you have singularities of certain types. I think it's very exciting that those questions are being addressed because those are fundamentally geometric questions. Yet, I still have on here the Abouzaid-Blumberg reference. That's a wonderful collaboration. As you all know, Mohammed is this outstanding symplectic topologist, and Andrew is an outstanding homotopy theorist. And by combining their talents and hard work, they were able to really resolve a lot of the technical issues that come about when you don't have when you do have singularities, you don't have smooth manifolds, or when you don't have framings, but maybe you have some other structure, like in the case they study, you had an almost complex structure. So one of the exciting things to me, as being somebody at the end of one's career, is seeing how symplectic topology and algebraic topology, that interface between these areas, becoming so large and so deep. It's not superficial, trivial stuff. It's deep. And I think that's absolutely fantastic. Mm-hmm. As to exactly what questions in symplectic geometry or in low dimensional topology or in differential geometry might be applied using these methods, that's beyond my expertise.
Okay, thank you very much. Any questions from anyone else?
Can I ask a question? Hey, Ralph.
David, hi, how are you?
Hi.
Good.
So getting back to the beginning of your talk, I had a question about coefficient groups. So, I mean, the beginning of your talk, when you were just talking about chain complexes and creating a homotopy object just from a chain complex, I assume you were assuming integer coefficients throughout that in order to start off with just sort of going from the algebraic side to creating a homotopy theory object. So I think a lot of times, people only have like Z2 coefficients or something. So does the coefficient group come into play? And like if you had a chain complex just defined over Z2 instead of Z, could you still create a homotopy theory object?
So yeah, that's a great question, and I'm glad you asked it. In some sense, having a stable homotopy object is the strongest kind of orientation possible. If you think just in terms of algebraic topology, if you have a chain complex with integer coefficients, then you can produce a chain complex with any other coefficients. But if you have a stable homotopy object, like a CW complex or even a spectrum, then you can produce a chain complex with integer coefficients. Similarly, you can produce, not chain complexes, but generalized homology theories that are oriented with respect to almost complex cobordism, or K theory, or some other generalized homology. The fancy way of saying it is stable homotopy is the initial object among all homotopy theoretic objects. So if you can get a framed manifold with corners description, or stable maps between spheres, then you can do any other kind of chain complex manipulation, including any sort of orientation.
But what about going back the other way? What about, again, at the beginning of your talk, you were starting with just a chain complex on the algebraic side, and then creating the homotopy theory side, right?
Right.
So and so if you have integer coefficients to start with, you can create this inverse system of spectra, which will then be, like you said, the object you really want. That'll then give you anything else you want. But what if you start with sort of less information on the algebraic side?
Yeah, that's a good question. I think you could develop a theory that's similar. If you just start with mod 2 coefficients, there are lots of different homotopy types that can realize the same chain complex with mod 2 coefficients. There's even, just like there's lots of different chain complexes over the integers that can realize the same chain complex over Z mod 2. So it's another layer of that you can put in. I don't believe it's a real complicated layer. It's more algebra than it is topology, which is not to say it's easy algebra, but it's something that one can approach algebraically, I believe.
Okay, thank you.
Sure.
Any more questions? Okay, if not, let's give Ralph Cohen one more hand.